In this lecture, we'll be discussing chemical kinetics, which is basically the rate of the reaction. And in this case, we'll be determining this rate by using a technique called titration. So if you remember last lecture, we were discussing the reaction of third-butyl alcohol with hydrochloric acid to form third-butyl chloride. This is actually a reversible reaction because chlorine is actually a leaving group as well. So you can go from this to this. It all depends on the concentrations of what you have. So adding water here will cause the alcohol to reform. So solvolysis of third-butyl chloride in water is a conversion of third-butyl chloride as to third-butyl alcohol, where the water acts as a reactant, right? So solvolysis is a type of reaction where the solvent, in this case it's water, acts as a reactant, and specifically if it's water, it's hydrolysis, which is where the water acts as the reactant. If you have a reaction where the alcohol is the reactant, then it's also alcoholysis. You can see on this slide a possible mechanism for how this reaction works. You have here your third-butyl chloride, and you have a slow removal of the chloride to form this carbocation. Now, because this is the slow step, this is what is known as the rate determining step. Because the next step is when water attacks this carbocation to form this oxonium ion again. And then chloride is used to remove the hydrogen, and you form your third-butyl alcohol. This solvolysis reaction is a nucleophilic substitution reaction. You see here the water acts as a nucleophile. In this particular case, as I mentioned, the rate determining step is the slow step. You have here, since this is SN1 reaction, it is unimolecular, right? So this is what the 1 stands for, is the unimolecular substitution, nucleophilic substitution reaction. As is the case with SN1 reactions, the rate of the reaction is unimolecular, and it depends on the concentration of the substrate, in this case the third-butyl chloride. So the concentration of the nucleophile has no effect on the rate of the reaction. And you can see this equation, if you remember from general chemistry, your rate is equal to K, a constant, times the concentration of, in this case, third-butyl chloride. So the SN1 here, in this case, is a first order reaction, because you have here just one, right? So continuing on the subject of reaction rate, let's say you have a concentration of third-butyl chloride at any time is equal to C in brackets, right? This concentration of C. So the rate of the reaction for this SN1 reaction is equal to K1 times concentration of C. The rate of loss of third-butyl chloride is equal to K1 times the concentration C, right? So then the derivative of the concentration with respect to time, negative, is equal to K1 times the concentration of C. So say at time 0, the concentration of third-butyl chloride is this again, right? We integrate the formula and we get negative natural log of concentration of C at time, whatever the time might be, divided by the concentration of C at the beginning is equal to K1 times the time. Okay, and so natural log of X is equal to 2.303 times the log of X, right? So here you have this negative 2.303 times the log, the normal log, the log base 10 of the concentration with time divided by the initial concentration is equal to K1 times T, or 2.303 log concentration of C after some time divided by initial concentration is equal to negative K1 times T. Right, so we just move the negative sign here, right? It's the same thing. So how exactly can this reaction be tracked? How can you find out what the actual rate is, right? Well, it turns out when you do this reaction with water, you end up producing hydrogen chloride here, right? and this can actually be measured by something called titration. So 1 molecule of tert-butyl chloride produces 1 molecule of hydrogen chloride. We will determine what the initial concentration is and the concentration with time in terms of the concentration of this hydrogen chloride. At the end, when the time is infinity, meaning the reaction is over, all the tert-butyl chloride will convert to HCl. So the concentration of HCl infinity, meaning at the end, is equal to the initial concentration of the substrate, right? So here we see T HCl concentration equals to initial concentration minus concentration with time, or concentration with time equals initial concentration minus the concentration of HCl with time, or the concentration with time is equal to the final completion concentration of HCl minus the concentration of HCl at a certain time. And you get this equation here, 2.303. You saw it from the last slide, equal to all times the difference of completion reaction, concentration of HCl minus concentration of HCl at a certain time divided by completion HCl concentration. And that is equal to minus K1 times T. So the value of the HCl at a certain time is determined by withdrawing an accurately measured sample from the reaction, which is referred to as an aliquot, right? And then you quench the aliquot with acetone, and then you try titrate with base. It's not necessary to use a standardized solution for base of the base for the titration, as long as the same base solution is used for all the titrations and the volume of all the aliquots are identical. Now, this is very important, right? All the volumes have to be the same. Otherwise, you won't get accurate readings. And additionally, it's not necessary to calculate concentration of HCl at time or at infinity, because the value is directly proportional to the volume of the base required to titrate the aliquot. So in this experiment, the base we'll be using is sodium hydroxide here, right? And you basically find the rate by doing 2.303 times the log of the volume of the sodium hydroxide infinity minus the volume of the sodium hydroxide at that certain time divided by the infinity volume, right? This is just the same equation, you just divide by 2.303 to get this. So on this slide, you see the types of things you will need for titration. You have here what is known as a burette, which has numbers going down instead of up, as you would expect. You clamp it, of course, so it's hanging down, and then you release your liquid on the bottom. This is a volumetric flask. This has a very exact volume. Both of these are very accurate instruments for measuring volumes. So you start off by preparing a solution of 0.04 normal sodium hydroxide, and you fill the burette, which is 50 milliliters. Next you prepare your stock solution. Use a plastic pipette to measure 1.2 milliliters of tert-butyl chloride into a 100 milliliter volumetric flask. Then you fill this flask to the mark, right? There's always a mark on these flasks, with H2O to propanol solution, and make sure you mix well. This is when you start your stopwatch, right? Because you're measuring the rate, so of course you need to time it. It will probably take around 75 minutes for this reaction to complete. So the next step is to prepare your infinity solution. Use a 10 milliliter pipette and take 10 milliliters of stock solution and put them into a 125 milliliter Erlenmeyer flask, and then you add 10 milliliters of water. As I said, be very careful with the volumes here. These are very important, otherwise you won't get accurate results. So the next step is the titration. So you'll be doing it at 10 minutes, 20 minutes, 35 minutes, 50 minutes, and 75 minutes. First step is at 10 minutes, use a 10 milliliter pipette and take 10 milliliters of stock solution in a 125 milliliter flask, add 10 milliliters of acetone to quench it, and then add 1 to 2 drops of bromothymol blue solution, which is an indicator, right? So your aliquot solution will look yellowish. Then you titrate with the 0.04 normal sodium hydroxide solution until the color changes to pale green. This is the end point. This is when the sodium hydroxide and the HCl have canceled each other out. And then you measure that volume, right? This is how you do the titrations. And you just keep repeating this every one of these minutes, and you'll end up getting all your different volumes for the different times. The next step then is to titrate the infinity solution. So you add your indicator into the solution of the infinity that was prepared in the previous slide until it turns yellow color. And then you titrate it with sodium hydroxide and you record the volume, right, that you used. You have to make sure you keep track of how much volume there was used to make the color change. So you can see here, you can prepare a table of 10 minutes, all the different times, right? And then you have here whatever volume you got, and then you use the equation to do all these calculations. Of course, you guys are not doing the experiment, so you don't need to do this, but you should be aware of how to do it, because it's important to know this for organic chemistry. So if you take those numbers that we got from the previous table and you plot them in Excel, you'll end up with a line here, and you'll notice that this line has a slope, and this slope is actually K1 divided by 2.303. So it should be the same. And if you see here the R squared value, if it is close to 1, that means it's a good linear fit. If it's not close to 1, that means it was not a very straight line. Okay. Other than that, this is how you can determine how accurate your results were for the rate of the reaction.